So what we're going to do in this video is just set up a very simple way of looking at the component parts of the weight acting on this slope from this mass M that's on the slope. Now, in most situations, what we're given is an angle of the incline of the slope, which in this case we're going to call theta, just so it's a generic angle. The mass of the object is m kilograms, which means the weight of the object, and you must remember this, acts directly vertically downwards to the centre of the earth, and we would call that mg. Most people get a little bit confused here, and they put the mg arrow going at right angles, which is incorrect. Everything acts directly to the centre of the earth, so vertically downwards. Now, in Unit 2, we didn't look at angles on forces on slopes. We only looked on the horizontal, so we usually worked in the horizontal and vertical. In this case, we now need to start thinking about forces components parallel to the slope and perpendicular to the slope. That's where everything's acting. So what we're going to do now is we're going to create a little right angle triangle, as we have done in the past. We've done forces around a point, and we're just going to create it like this. So we have a perpendicular component here to the slope, and we have our parallel to the slope here, so they meet at right angles. Now, the one thing we can always put in straight away is this angle here. By using similar triangles, this angle is theta. The reason being quite easy. Obviously, if the weight mg acts directly to the centre of the earth, it creates a 90-degree angle with the base of this incline. So if we have a 90-degree angle there and theta here, this angle here must be 90 minus theta for it to add up to 180 in that triangle. And because this force here is acting at 90 degrees to the slope, this angle must be theta, therefore, to make the 90-degree angle. Now, using trigonometry, you should be able to work out now that given mg is the hypotenuse, the 90-degree angle to the slope will be mg cos theta, which is the block pushing into the slope, and mg sin theta is the component of this weight acting down the slope. So what we would tend to do here is two things. We'd immediately annotate the diagram with mg sin theta here, and we'd also put r is equal to mg cos theta here. Now, this can change the reaction depending on what else is acting on this object, but in a very simple case, this is what would happen. These would be the first stages of your analysis of this object, and in later videos we'll start adding different things in. Be reminded, though, that we will also be using things like friction, so our coefficient of friction being mu. Obviously, if our mu frictional force was acting up the slope, that would be mu r, which is mu mg cos theta. And be mindful that if mg sin theta is greater than mu mg cos theta, then we will achieve an acceleration down the slope. Because obviously there's a change in force. If, however, mg sin theta is equal to mu mg cos theta, we'll have what we're called that limiting equilibrium, where it's on the verge of moving but not quite. And then the one that most people struggle with, mg sin theta less than mu mg cos theta, the block stays still. It's static, it doesn't move, because you have not